So imagine for a second that you are holding like a simple, solid wooden building block, just a regular block.
Okay, I'm picturing it.
And you've been told your entire life that this block is, the smallest, most fundamental piece of the universe.
Right, but you can't break it down any further.
Exactly. You can't break it. You can't alter it. It just is. It's the absolute bedrock of reality.
Which, I mean, there's a deep psychological comfort in that idea, you know?
Oh, absolutely.
For centuries, science basically operated on the assumption
Yeah.
that at the very bottom of everything, there were these unbreakable rules, just indivisible materials, a completely static, permanent foundation.
Well, today's deep dive is all about the man who basically smashed that wooden block to pieces.
Yeah, he really did.
We're talking about a farm boy from New Zealand named Ernest Rutherford. And our mission today, using this massive, highly detailed Wikipedia article as our source, is to figure out how he dismantled that static reality.
Right, because he looked at that indestructible foundation, realized it was mostly empty space, and proved it by literally breaking the universe apart.
It's just wild. His work replaces this static idea of matter with something that's dynamic, volatile, and just deeply strange.
His entire career is really a masterclass in challenging established truths. I mean, before Rutherford, atoms were just considered the unchanging building blocks of chemistry.
Yeah, totally static.
Exactly.
Yeah.
But through this rigorous, like almost obsessive experimental data, he forced the scientific establishment to accept that matter can spontaneously transform.
And the path he took to become the father of nuclear physics is so fascinating because, he wasn't born into these aristocratic scientific circles.
No, not at all.
He was born in 1871 in Brightwater, New Zealand. And fun fact, the official records actually show his birth certificate mistakenly spelled his name Ernest, like with an A.
Oh, really? I love that. It actually perfectly captures his personality, right? That relentless, earnest drive he had.
Exactly. He was the fourth of 12 children to an immigrant farmer and a school teacher. So he had to secure multiple scholarships just to keep his education going at Nelson College and then Canterbury College.
And he studied a little bit of everything, didn't he?
Yeah, a massive spread. Latin, English, maths, physical science, chemistry, geology. Just a huge interdisciplinary background.
And that background forged a very specific kind of thinker.
Mhm.
You know, he wasn't just a theorist locked in a room doing math problems.
Right.
He was a practical builder. That hands-on capability became his defining trait, especially when he won the 1851 Research Fellowship in 1895.
Which was huge for him.
Oh, massive. That fellowship allowed him to travel to England for postgraduate study at the Cavendish Laboratory at the University of Cambridge.
But when he arrived at Cambridge, he was actually classified as an alien.
An alien?
Yeah, that was the actual bureaucratic term they used. It meant he was a researcher allowed to study there without having a prior Cambridge degree.
Wow. Talk about imposter syndrome.
Right. He was stepping into literally the most elite scientific institution in the world as a total outsider. And he's studying under the legendary J.J. Thomson.
And the funny thing is, he didn't even focus on atoms right away. He started out tinkering with radio waves.
Yeah, he had brought this specialized magnetic detector that he designed back in New Zealand.
And the mechanism for that was just ingenious. He used these magnetized steel needles that would actually, they'd lose their magnetization when subjected to high-frequency radio waves.
Oh, interesting.
Yeah, so by measuring that loss of magnetism, he could detect electromagnetic waves across distances.
And he actually managed to detect those radio waves from half a mile away, which, for a brief moment, gave him the world record for wireless transmission distance.
For a very brief moment.
Yeah, very brief, because then Guglielmo Marconi comes along with a vastly superior system and transmits a signal nearly 10 miles.
Right, completely obliterating Rutherford's record.
It's like, imagine a self-taught coder from a rural farming town walking into a top-tier Silicon Valley incubator today, right?
It's okay.
They build this incredible app, and then the very next day, a major tech giant releases something 20 times better.
That's a great way to put it.
But here's my question. He was literally outdone by Marconi almost immediately. Did losing that radio race actually force him to pivot toward his true legacy?
Oh, absolutely. I completely agree with that. Because looking at the timeline, losing that race wasn't a failure at all. It was essentially an audition.
An audition for Thomson.
Exactly. Thomson watched Rutherford build this meticulous, highly sensitive apparatus and immediately realized, okay, I have a world-class experimentalist on my hands here.
And Thomson needed exactly that kind of guy.
Right, because Thomson was deeply involved in studying the electrical conductivity of gases, specifically when exposed to X-rays, which were brand new at the time.
Right, X-rays were the hot new thing.
Yeah, and he needed someone with Rutherford's exact skill set to design the apparatus for these experiments. That partnership actually led to the discovery of the electron. And then, when Henri Becquerel published his findings on the mysterious energy being emitted by uranium, Rutherford was just perfectly positioned to pivot.
He had all the right tools?
Exactly. He took that same rigorous methodology he used for measuring radio waves and just applied it to this bizarre new phenomenon of radioactivity.
So then he takes a chair at McGill University in Canada, and he starts categorizing this strange radiation.
And he realizes it's not just one uniform beam of energy.
Right. He separates them based on how they interact with matter. And this is where he coins the terms alpha ray and beta ray.
So it's iconic terms.
Yeah, and he didn't just name them, he characterized their physical properties. So alpha rays were incredibly easy to block, like a single sheet of paper could stop them.
Because they were massive and carried a positive charge.
Exactly. But beta rays were much lighter, carried a negative charge, and could punch right through a thin sheet of aluminum. And then later on, he categorized a third type, the gamma ray.
Right, which was an incredibly high-energy electromagnetic wave. You needed thick lead to stop that one.
Yeah. I mean, just categorizing those rays would have secured his legacy, but Rutherford was interested in the source of the rays.
Yeah, where was it all coming from? Working alongside the chemist Frederick Soddy, he started focusing on the radioactive element thorium.
And they noticed something weird, right?
Very weird. Thorium was emitting this mysterious gas. So they subject this gas to a whole battery of chemical tests, and they managed to eliminate every known normal chemical reaction.
So what was left?
They arrived at a conclusion that completely shook the foundations of chemistry. The thorium atom was spontaneously disintegrating and leaving behind an entirely different element.
Which we now know as radon.
Exactly.
Wait, let's pause here, because if all of science at this time believed atoms were the indestructible basis of matter, didn't this sound like absolute heresy? How did they not get laughed out of the room?
Oh, it sounded completely like heresy.
Yeah.
But the thing is, the data was simply undeniable. They proved radioactivity wasn't just like magic energy radiating from nowhere.
It was physical pieces.
Yes. It was the atom literally breaking apart. And this forever shifted the paradigm of both chemistry and physics. They published this as the law of radioactive change.
And there's this incredible mathematical precision to this disintegration that completely defies logic. Working with RBONs, Rutherford actually discovers the concept of the half-life.
Which is just a massive conceptual leap.
Yeah. He observed that a sample of radioactive material, regardless of its total mass, took an exact, predictable amount of time for half of it to decay.
And the profound implication there is that it introduces a probabilistic nature to the physical world. It literally lays the groundwork for quantum mechanics.
How so?
Well, if you have a lump of thorium, you cannot look at a single individual atom and predict when it's going to decay.
Oh.
The individual event is entirely random.
Right, you have no idea.
But when you zoom out to a macroscopic level, millions of those random events coalesce into this unshakable mathematical certainty. Half the lump will be gone in an exact time frame.
It's like a macroscopic clock powered by microscopic randomness.
That's a brilliant way to put it.
Yes. And that predictable release of energy actually solved one of the most vicious scientific debates of the era.
Oh, the Earth's age debate.
Yeah. You had biologists like Charles Darwin arguing that evolution required the Earth and the Sun to be hundreds of millions of years old.
Right.
But the physicists, led by Lord Kelvin, calculated the cooling rate of the Earth. They assumed it started as a molten sphere and determined the planet could not possibly be older than 20 to 40 million years.
So the physics simply didn't allow for Darwin's timeline.
Exactly. But Kelvin's math was entirely correct based on one massive assumption that the Earth had no internal heat source.
And that's where Rutherford steps in.
Yes. And he actually did this during a lecture where Kelvin himself was sitting right there in the audience.
Oh, that must have been tense.
Very. Rutherford points out that radioactivity, this new phenomenon where atoms continuously release energy as they decay, acts as an internal heater for the Earth.
Right. That ongoing radioactive decay completely disrupted Kelvin's cooling calculations.
Exactly. It proved the Earth and the Sun could be billions of years old, which perfectly aligned the physics with Darwin's biology.
It's amazing how one discovery just rippled through every other scientific discipline.
Seriously. So once you establish that atoms are shooting pieces of themselves outward and generating massive amounts of heat, the inevitable next question is, what does the architecture of this atom actually look like?
What's inside the wooden block?
Right. So Rutherford moves back to Britain, to the University of Manchester, and he orchestrates the most famous experiment of his life in 1909, the gold foil experiment.
But wait, before he could fire his alpha particles at the gold foil, he had to definitively prove what an alpha particle actually was, right?
Right, because up until then, they were just these mysterious heavy rays.
And the elegance of that proof is just staggering.
Huh.
Rutherford and Thomas Royds placed radon gas in a glass tube, but the walls of this tube were just thin enough to allow alpha particles to pass through, but thick enough to block the radon gas itself. Then they surrounded this inner tube with an evacuated outer glass tube. Over several days, the alpha particles shot through the thin glass and slowly accumulated in the outer tube.
And then what?
Rutherford passed an electric spark through that accumulated gas and studied the light it emitted using a spectroscope. And the light showed the unmistakable yellow spectral lines of helium.
Wow.
Yeah. He had trapped the mysterious rays and proved they were physical matter specifically. They were helium nuclei.
So now he has his ammunition. He knows alpha particles are heavy, fast-moving, and positively charged.
Right.
He works with Hans Geiger and Ernest Marsden to fire these heavy particles at a piece of gold foil that's been beaten down to just a few atoms thick.
And to understand how crazy the results of this were, we have to remember the reigning theory of the atom at the time.
Right, J.J. Thomson's plum pudding model.
Yeah. Science believed the atom was this soft, uniform sphere of positive charge with negative electrons dotted throughout it, literally like plums in a pudding.
So if that were true, firing a heavy, high-speed alpha particle through it should be like firing a bullet through a cloud of smoke, right?
Exactly. The particle should just tear straight through with almost no resistance.
So what actually happened?
Well, Geiger and Marsden spent hours sitting in a pitch-black room, literally waiting for their eyes to adjust to total darkness, just so they could stare at a zinc sulfide screen.
That sounds miserable.
It was incredibly tedious. Every time an alpha particle hit the screen, it produced a microscopic flash of light. And they were manually counting these flashes.
And at first it went as expected, right?
Yeah, the vast majority of the particles zipped right through the gold foil and hit the screen dead center.
But then they start seeing flashes off to the extreme sides. And incredibly, some particles bounced almost straight back toward the source.
Which is just, it's mind-blowing. Rutherford famously said, "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you."
I love that quote. It's like, imagine you're blindfolded and you're throwing a handful of tennis balls, or let's say heavy bowling balls, into a dense layer of fog.
Okay, bowling balls into fog.
You expect them to just pass straight through and hit the wall behind the fog, but suddenly one of your bowling balls ricochets backward and smashes into your shin.
Ouch. Yeah.
The only logical conclusion is that hidden somewhere inside that fog is a tiny, incredibly dense anvil.
That is a perfect analogy. And that hidden anvil is the atomic nucleus.
Right.
Rutherford deduced that almost the entirety of an atom's mass, along with all of its positive charge, has to be concentrated in a center so unimaginably small that the vast majority of the alpha particles just sailed right past it without hitting anything.
So the atom wasn't a solid block at all.
Not even close. It was almost entirely empty space, anchored by a dense central core. And this singular insight just destroyed classical chemistry and birthed the modern nuclear model of the atom.
But discovering the nucleus wasn't enough for him. He immediately transitions from observing the nucleus to actively tearing it apart and reassembling it.
Yeah, you couldn't just leave it alone.
In 1917, he initiates this era of playing like universal Lego. He creates the first artificially induced nuclear reaction.
How did you do that?
He sets up an experiment where he bombards pure nitrogen gas with his trusted alpha particles. The nitrogen nuclei absorb the alpha particles, but the resulting structure is way too unstable to exist, so it immediately ejects a positively charged particle.
And the math of this reaction is where the magic really happens. A nitrogen nucleus has 7 protons. The incoming alpha particle, which we know is a helium nucleus, brings 2 protons.
Right, 7 plus 2.
Exactly. That creates a highly unstable state of 9 protons. The nucleus violently ejects 1 proton to stabilize itself.
Or in a nucleus with 8 protons is oxygen.
Yep.
Hold on, he turned nitrogen into oxygen? Isn't that literal alchemy? Why isn't he universally known as the guy who finally achieved the alchemist's dream?
Well, in a way, he is. I mean, that's why he's the father of nuclear physics. He proved that humans could artificially transmute elements, increasing a nucleus's mass through collisions.
That's just wild. And he officially names that ejected single positive particle the proton in 1920.
But when you look at a nucleus packed with protons, a glaring physics problem emerges.
The electrostatic repulsion.
Right. Every proton carries a positive electrical charge, and identical charges violently repel one another.
Like trying to push the positive ends of two magnets together.
Exactly. So if you pack multiple protons into a space as tiny as an atomic nucleus, the repulsive force should blow the nucleus apart instantly. It literally cannot hold together on its own.
And Rutherford realizes this immediately. In 1921, working alongside Niels Bohr, he reasons that the nucleus is heavier than just the weight of its protons, and yet it remains completely stable.
So there's a missing piece of the puzzle.
Right. Therefore, there must be an unseen, uncharged particle hiding inside the nucleus, acting as a buffer to keep the protons from tearing each other apart.
So he just deduces it.
Exactly. He theorizes the existence of the neutron purely through deductive logic. He couldn't see it, his instruments couldn't measure it, but the architecture of reality demanded that it exist.
And it took over a decade of technological advancement before his associate, James Chadwick, could definitively isolate and prove the existence of the neutron in 1932.
Which earned Chadwick a Nobel Prize, by the way.
It's just a testament to Rutherford's ability to deduce the unseen mechanics of the universe based on secondary effects. It was unparalleled.
Truly. But his brilliance wasn't just confined to abstract atomic theory.
Oh no, during World War I, he got very practical. The British military desperately needed a way to detect submerged German U-boats. So Rutherford threw his massive energy into acoustic research.
Yeah, he collaborated with the French physicist Paul Langevin on using piezoelectricity.
Which sounds complicated, but it's really cool. The mechanism basically involves using specific crystals that generate an electrical voltage when mechanical stress is applied to them.
Like when a sound wave hits them.
Exactly. And conversely, they change shape when an electrical current is applied.
So Rutherford built and refined experimental apparatuses to measure acoustic waves underwater using these crystals.
And while Langevin's specific transducer design became the operational standard for submarine detection, it was Rutherford's rigorous groundwork that directly enabled the development of modern sonar.
And by extension, the ultrasound technology used in hospitals today.
Right. His versatility was just staggering. He moved seamlessly from the most abstract theories of the cosmos to the gritty, practical engineering of underwater acoustics.
But for all his vision, he harbored a fascinating blind spot regarding the ultimate destiny of his own discoveries.
Oh, the moonshine comment.
Yes. This brings us to 1933. Two of Rutherford's students, John Cockcroft and Ernest Walton, achieved a monumental milestone. They artificially split the atom using a massive particle accelerator.
Proving that enormous amounts of energy are locked inside the nucleus.
Exactly. So following this breakthrough, Rutherford delivers a public speech at the British Association for the Advancement of Science. He acknowledges the immense energy of the nucleus, sure. But he points out that the particle accelerator requires vastly more energy to run than the splitting atom actually releases.
Right, the net energy was negative.
So he tells the press that anyone looking for a new source of commercial power from atomic transformations is talking moonshine, basically saying it's nonsense.
He really viewed the atomic nucleus as a domain of pure scientific inquiry, not a practical power plant. He looked at the vast inefficiencies of the early accelerators and concluded that humanity would never extract more energy out of the system than we put into it.
So the concept of a self-sustaining reaction simply wasn't on his radar.
Not at all.
It's a wildly ironic moment. It's the equivalent of an engineer inventing the microchip, looking at it, and confidently stating it will only ever be used to make slightly better digital watches.
Even the ultimate genius has a blind spot, right?
No.
He completely missed the implications of his own life's work.
But that blind spot is exactly what catalyzed the next leap in physics.
Yeah, this is my favorite part of the story. A brilliant Hungarian physicist named Leo Szilard was living in London at the time, and he read a summary of Rutherford's moonshine speech in the Times.
And Szilard was not the kind of guy who liked being told things were impossible.
No, he was inherently rebellious. So reading the great Ernest Rutherford declare something impossible intensely irritated him.
The story goes that Szilard was walking down Southampton Road just fuming about the article, and as he waited for a traffic light to turn green, the solution hit him.
The chain reaction.
Yes, he realized that if you could find an element that absorbs one neutron and then ejects two neutrons as it splits, those two neutrons would hit other atoms, ejecting 4, then 8, then 16.
It wouldn't require an inefficient particle accelerator at all.
Exactly. It would power itself.
Rutherford's dismissive moonshine comment directly provoked Szilard into conceiving the nuclear chain reaction.
That's incredible.
Rutherford cracked the atom open. But it was his public skepticism that accidentally challenged the next generation to unleash its power. It really highlights that scientific discovery operates just like the chain reaction Szilard envisioned.
How so?
Well, a scientist uncovers a fundamental law, publishes it, and it bounces outward, striking other minds, accelerating in directions the original discoverer could never predict or control.
That's a beautiful way to look at it. Sadly, Rutherford didn't live to see the atomic age he inadvertently set in motion. He died in 1937 at the age of 66.
And the cause of death was surprisingly mundane for a man who mapped the extreme forces of the universe.
Yeah, a small hernia that he neglected until it became strangulated.
The scientific community immediately recognized the scale of what they had lost. He was buried in Westminster Abbey, and his ashes were placed in the nave just a short distance from the graves of Isaac Newton and Charles Darwin.
That's some serious company. And decades later, in 1997, the scientific community permanently etched his name into the periodic table, officially naming element 104 Rutherfordium.
Which is really the ultimate honor for an experimentalist who spent his life deciphering how elements transform.
So bringing it all back, the story of Ernest Rutherford is fundamentally about the courage to dismantle your own reality.
Absolutely.
Being well-informed isn't just about memorizing the current textbook. It's about looking at the indestructible assumptions within your own industry, your own beliefs, or your own field of study, and asking the dangerous question.
What happens if I fire a shell at this?
Exactly. What if this solid wall is actually just empty space?
That willingness to break the mold is definitely his scientific legacy. But there is a deeply human element to his story that often goes entirely unnoticed, and I want to leave you with this thought.
Okay, lay it on us.
In 1938, the astrophysicist James Jeans delivered a eulogy for Rutherford at the Indian Science Congress. We have this pervasive cultural trope of the solitary, tortured genius locked away in a dark laboratory, wrestling with the universe completely alone, right?
Right, the lone mad scientist trope.
Jeans completely shattered that image. He described Rutherford not as an isolated mastermind, but as an energetic, happy warrior.
The records show Jeans specifically highlighted Rutherford's capacity to direct and inspire a band of enthusiastic coworkers.
Yes.
He wasn't just a boss in a lab, he was a catalyst for the people around him.
And that leads to a profound question I want you, the listener, to consider. We know Rutherford's intellect changed the world. But given how many Nobel laureates he trained, and how his laboratory functioned as an incubator for the greatest minds of a generation, could it be that his ultimate scientific tool wasn't his intellect at all? Perhaps his greatest asset was his joyful, unyielding enthusiasm for human connection and collaboration.
That's a great point.
He proved that the atoms making up the universe are deeply interconnected and dynamic. It turns out the exact same thing is true for the minds that discover its secrets.
What an amazing parallel to end on. Thank you for taking this deep dive with us today. Keep questioning the building blocks around you.